Okay, so we did hypothesis testing for means, a single mean, and we did it in two ways. We did it when we knew what the population standard deviation was, and we used the z term for a test statistic. And then if we didn't, we would use the sample standard deviation and the t statistics and the degrees of freedom of the problem to come to our conclusions. But now we're going to look at proportions. And proportions are different than means, and we've already done proportions a number of times. First time we encountered proportions was when we worked with the binomial distribution. And then again with confidence intervals, we did confidence intervals of proportions. So now we're going to use proportions. We're going to do hypothesis testing of proportions. And just as a review, our proportion might be represented by these sorts of statements. For example, 5% of people struck by lightning were standing under a tree. So that means 95% weren't standing under a tree, according to the claim. So P equals 0.05 there. The 30% of tornadoes prove at least one fatality, and 75% of Americans own a car. So these are all statements that have two outcomes, a success and a failure type situation. So all of these, all our proportions can be looked at as proportions. For example, you'd have some variable or some certain number of things divided by the total number, and that equals P. Usually that's considered our success. P is our success. So if you have a P, you can have a Q, which is 1 minus P. But if we're looking at this P, we could, let's just say like here, turn that into a K, like say 3 out of 100 or 0.03, that could equal our P, for example. If we're saying that's a success, or maybe 20 out of 200, 0.10 could equal our P. So this really should just be review for you. Everything I've discussed so far to this point. So, and for some further review, we know that for proportions, we had both population and sample terms. So P was a population proportion. And for a sample, we put a hat on it. P is a sample proportion. It's like Portlandia. Put a hat on it. Okay, so P hat then is just going to be X, some X over N value. So this is like the number, let's just call this success, the number of successes. This will be like our sample size. Okay, then, going along with that, Q hat equals 1 minus P hat then. Which we could also think of as our sample size minus the X values for success. So that's everybody else over N. So these are always binary in ideas. And P hat plus Q hat equals 1. Do that in red. Just recall that. P hat plus Q hat always is going to equal 1. You either have P hat or you had Q hat. Little note. Finally, recall that for our binomial distribution, that the population mean was equal to n times p, and the population standard deviation was equal to the square root of n times p times q. It's always easy to calculate. Much easier than standard deviations for means. So if z equals x minus mu over sigma, now this is not x bar, so this is not sigma over square root of n. This is z in terms of the variable x. Then for proportion, we already talked about this. Z with confidence intervals, z equals x minus np over square root of n pq. And I guess I didn't derive this back then, but we could look at it this way. I could multiply this by 1. I could multiply this idea here by 1, or 1 represented by 1 over n over 1 over n. Anything over itself is equal to 1 times x minus np over square root of npq. And this will end up being x over n minus p over square root of npq over n, which we already said x over n is p hat. So that's how we get this, p hat minus p over, and then I can squeeze this into square root of npq over n squared. So this is ultimately going to be p hat over p minus square root of n, or square root of pq over n. So that's how we get this z term. I should have probably derived this before. So this is going to be the z term we use now for our test statistic. So this will be our test stat in our hypothesis analysis, which we're going to do the exact same way as we did before, except we're going to use this as our test stat when it comes time. And we will calculate our critical region in exactly the same way and do the mechanics of our hypothesis testing in exactly the same way. And I will demonstrate that now with an example problem. Okay, here's our problem. Based on info from the Center for Disease Control, 70% of young people are obese. Well, we want to test that claim. So we get a random sample of 200 young people, and we find that 42 were obese in our random sample. So let's go ahead and set up some of our parameters here in statistics. So first off, n, our sample size, is what? 200. We had 200 in our sample size. Okay. And our sample number, 42. Let's run this. I didn't say this, but let's do this level of significance 0.05. All right, so just with that information alone, I can look up here and I can see that our population, P, is 0.17. So I pulled that from here, which means that Q equals 1 minus 0.17 equals 0.83. Okay, that was our population. Our sample, P hat, is 42 over 100. 42 over 200, I mean. So that's 0.21. And Q hat then is going to be 1 minus 0.21. Which is 0.79. Okay, so let's set up our analysis here. First off, we're going to figure out our H naught and our alternative hypothesis. So for H naught, our proportion equals 0.17, and our null hypothesis is that it doesn't equal 0.17. So this is going to be a two-tailed test. Okay. Let's come up with our test statistic. Here's the formula for our test statistic. So we're just going to cookbook plug and chug. So P hat is 0.021. We're pulling that from here. Minus P, 0.17 over the square root of 0.17 times 0.83 divided by 200. Okay, you do the math here. This equals 1.51 approximately. Okay. Let's compare to our critical region. So if alpha equals 0.05, alpha over 2 is 0.025. Our degrees, well, we don't have degrees of freedom. So here's our two-tailed, what two-tailed will look like. This area on either side here is going to be 0.025. So that means our Z crit is going to be plus or minus 1.96. Okay, plus or minus 1.96. Now we go ahead and we compare our test value. So our test value is 1.51, 1.51. So if this is 1.96, this equals minus 1.96, and 1.51 falls in here. So since our test stat, did not fall in the critical region, we do not reject the null hypothesis. So since our null hypothesis is that P equals 0.17, we might make this claim. There is not enough convincing evidence to reject the idea that the or that 17% of young people are obese. And that's all I have time for.